I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. And none will be so difficult or expensive to accomplish.
It's one small step for man, one giant leap for mankind.
Yeah, my name's Clive Neal. I'm a professor of lunar geology at the University of Notre Dame in Indiana. And I'm going to talk to you today about the crust of the moon and lead you on a journey of what we've understood from Apollo and since Apollo and why we should go back. Going back to the moon is going to be important for a number of reasons, not least of which is science, but also more importantly for exploration and maybe the economy. Creating jobs outside of NASA, that is off-planet, becomes a reality if we then use the moon as an enabling asset to then go to Mars. So understanding the moon becomes very important, not only about how the moon formed, but what is available on the moon that we can use to make the moon that enabling asset. So if we look at the moon, we already know that it's the closest planetary body to Earth. And you can also see in relative to the other planets that the moon is the smallest planetary body. So being small, it means its heat engine shut down a long time ago. We know from Apollo that the surface of the moon is very old, maybe 3 to 4 billion years old. There is no atmosphere on the moon anymore, but what we have is meteoroid impacts. So if we look at the moon then, the moon represents an end member because the earliest stages of differentiation, how that planet evolved soon after formation, is now frozen in time. And it gives us then an end member to look at how Earth, Venus, Mars, and Mercury could have also evolved. So if you look at the moon, you can see here we've got the near side and the far side from the Lunar Reconnaissance Orbiter camera, the wide-angle camera. These are mosaics that have been put together, and there are very notable differences between the near side and the far side. You can see on the near side we have lots of areas which are darker. These are seas or mare that were formed by basalt erupting onto the surface 3 billion years ago, although we now know maybe just a few 100 million years ago. If we look at the far side, it is very different. We can see that it is dominated by the Highlands crust material, much lighter material, because the Highlands crust is made up of this mineral called plagioclase, a calcium aluminium silicate. And we see this distributed across the moon. Very few areas of mare on the far side because the crust there, we now know, is much thicker than it is on the near side. So if we then take a very broad brush look at our moon, we can see that we have our mare or maria on the near side, where we've had eruption of lavas onto the surface and resurfacing of much of the near side of the moon through these eruptions. We then have these highlands crustal areas which are dominated by the mineral plagioclase. So if you go out at night and you can see the moon, the lighter areas represent those highlands crustal areas. This is a very old surface of material, some parts of which were actually formed during the initial formation and differentiation of that particular planet. Another important feature are these impact craters. You can see here we've got one into the Maria and one into the highlands areas, but this means that our moon has been under attack pretty much since it formed by impacts that don't burn up because there's no atmosphere on the moon. So they go in and they can redistribute material around the moon and redistribute that crustal material that we sent Apollo astronauts to pick up and bring back. So if we look at the samples that we have from the moon, you can see that the landing sites for Apollo and the Soviet lunar robotic return missions are highlighted here. You can see that the Apollo samples are collected all from the near side and the central near side, with the lunar 16, 20, and 24 missions going to the eastern limb of the lunar near side. Now, these Soviet lunar missions only brought back less than a kilogram of material, whereas the Apollo missions brought back a total of 382 kilograms of material. Now, in the late 1980s, we recognized that meteorites in the collection were actually derived from the moon. We compared compositions that we had from Apollo samples with those from the meteorites, and we can actually see that these were derived from the moon. But as I said earlier, exactly where on the moon, we just don't know. But they are giving us a new look at the moon and starting to cast some doubt on some of the conclusions drawn by just looking at the Apollo samples. Since Apollo, we've had a lot of orbital missions that have gone around the moon and given us global data sets of the entire moon. With those data sets, we can now define different terrains. You see in the diagram, we have PKT and FHT. PKT means the Procellarum creep terrain. The FHT is the feldspathic highlands terrain. So if we deal with the PKT, this is a very special area because it is enriched in this component we term creep. Now, creep, K-R-E-E-P, represents potassium, rare earth elements, and phosphorus in terms of our signature that we have there. Now, what it means is that we have a lot of materials that are enriched in these elements in the PKT. If you go outside there into the feldspathic highlands terrain, they are much lower abundance, if not devoid of that particular signature. So it showed us that we had distinct terrains, that the moon was not as homogeneous as once thought. And then when we look at these global data sets in relation to the Apollo samples that were brought back, we can see that the Mare basalts in the Apollo collection showed a bimodal distribution on the basis of titania. Now, if we then look at the compositions of basalts from the remote sensing data, we see that no, it's not a bimodal distribution. By far, the most abundant type of basalt is the low titanium Mare basalts. And in some cases, these data sets are defining lithologies that we just don't have any examples of. And we'll come back to that in a little bit. Before we start looking at the crust, lunar crust itself, we have to look at the origin and early evolution of the moon in order to understand where the crust came from, what we actually go out and can see from this planet when we look up at the moon. We need to understand how it formed. Now, we've been informed by samples that came back from Apollo, and it was right after the Apollo 11 samples were returned that the idea of a magma ocean was born. Now, the formation of a magma ocean requires a lot of energy. In looking at how the moon orbits the Earth, the only way that it can really achieve those particular orbits and those orbital dynamics is to be formed at a very violent origin in terms of a collision between two planetesimals early on in the origin of the solar system. You see here depicted that a cataclysmic impact between these two planetary bodies. We have the proto-Earth, and then we have the Mars-sized planetesimal that came in and hit it. And most of the material from the crust and the mantle of both planets was ejected out and coalesced to form the moon that now orbits us and we can go out and see. But the energy involved in both the impact between the two planetesimals and then the accretion of the material to form the moon meant that it was very hot and formed this magma ocean. Now, this magma ocean means we had a lot of energy being involved and a lot of evaporation, and it may even be that the moon had a very thick but metal-rich atmosphere during this magma ocean time. As the moon started to cool down, we started to get this quench crust. And I don't know if you've ever seen videos of lava pools on Hawaii, but there's a lot of convection going on, and these quench crusts get taken back down into the magma and assimilated back into it. So this was a very temporary crust until the quench crust could thicken and then maintain its integrity rather than being torn apart by the convection of the magma ocean. Now, as the magma ocean continued to cool, we started to see minerals come out of it. Those with the higher melting point would crystallize first. Those that had a density greater than that of the magma would sink and form the mantle of the moon. As the evolution of that magma ocean continued, we started to see different minerals precipitating out as the magma composition changed. Eventually we had this wonderful mineral plagioclase crystallized, and plagioclase would have been less dense than the magma, so it would have floated. And you could see in the blue area on the diagrams where that plagioclase would float to the top. It would sit underneath that quenched crust lid, the primordial crust itself, and we now call that plagioclase crust, well, maybe the primordial crust, because we actually can have samples of it, and we'll get to that in just a little bit. The other thing I want to point out here is this creep name again that comes out. This is the last dregs of the magma ocean. As the magma ocean crystallizes, the elements that don't go into the crystals become concentrated into the residual magma. So the potassium, the rare earth elements, phosphorus, thorium, uranium, all become concentrated in this creep component, and it becomes one of the signatures that we know, if we're going to model this magma ocean, that we have to then replicate. So we'll focus on the rare earths because these are an important series of elements in the periodic table. These are the lanthanide series, and we can see that they're divided into the light and the heavy rare earths. I'm going to be referring to the light and heavy rare earths as we continue on. So if we look at our mineral plagioclase, now plagioclase likes europium. And when plagioclase forms, it will actually incorporate the europium in the 2+ form much more than the other rare earth elements. So what we end up with in the top profile here is we can see that plagioclase will have a positive europium anomaly. That means then that the magma from which that plagioclase came from now has a negative europium anomaly. And we see this negative anomaly in all the Mare basalts that are erupted, suggesting that their source has seen this plagioclase with removal. The other important thing about the rare earth elements are samarium and neodymium. You can see those highlighted here, and one of the isotopes of samarium decays to the 143 isotope of neodymium at a constant rate. This radioactive decay is very important when we come to age dating these very ancient samples that have been brought back from the moon. So in our lunar magma ocean model then, and this is just a model, and there have been several attempts to actually show what proportions of minerals came out and at what time. Now this is going to be dependent upon our magma ocean starting composition. And you can see here there are 5 models that are shown in the diagram. And what I want to point out is the point at which our plagioclase-rich crust could start to form. Now, basically what this tells us is that the magma ocean has to be 2/3 crystallized before we can start to have plagioclase forming. This means we would have a very thick quenched crust lid sitting on top of that magma ocean, but we would also have this pressure on the crystals as they were being formed. So we would have then a long time between initiation of magma ocean and formation of the crust that we can now see from Earth. So you can see here the diagram shows that we have an initial quenched crust until we get plagioclase, and then plagioclase would float and sit beneath that quenched crust until it is exposed through the meteoroid impacts that we can still see evidence of and still see it happening today through impact flashes. So our crust then, the initial crust would have been this quenched crust. The lunar magma ocean crust forms after a while when we start to see plagioclase crystallizing out of that magma ocean. Now another mineral that is also important in our modeling is garnet. Now garnet, like plagioclase, is an aluminium-rich mineral, but it needs to form at pressure, and on the moon it has to be below about 500 kilometers. Now garnet retained in the source gives important information or imparts important information on the magmas that are then produced, because what we see with garnet, you can see the mineral incorporates the heavy rare earths over the light rare earths. So if you extract garnet from a melt, you will enrich the melt in the lights and deplete it in the heavies. Conversely, if you have garnet in the source region and you melt it and retain garnet in the source region, that melt will be enriched in the light rare earths and depleted in the heavies. So we can use that then to take the 5 magma ocean models to look at what happens to our rare earth element sequence. And as we go through here, you could see that they're modeling the different percentages that come out. And in this model from Snyder et al. 1992, the creep signature, which are the red squares in each one of these diagrams, is best modeled if 3% garnet is also extracted from the magma ocean along with plagioclase. If we then look at the Elkins-Tanton model of 2011, we can see the same sort of thing, that garnet gives you a much better representation of the creep that we know exists on the moon. If we then look at the Lin et al. Model, this is a bit different. They used anhydrous conditions, and what we see here is that some garnet is required, but eventually it needs to, as the mantle fills up with these crystals, we get a reduction in the amount of garnet to nothing. But if we then combine the small amount of garnet and in the early stages of plagioclase crystallization, we then see it disappear towards the end. We can pretty much recreate that creep signature. Similar sort of thing with the Charlier et al. Model in 2018. And interestingly, the Rapp and Draper model of 2018 does not require any garnet to generate that creep. So you can see these are all models. They are giving similar signatures, but how we get there is very different. So there are a lot of questions in how the magma ocean differentiated and also how the lunar crust formed. So what have we learned from Apollo? So what we have here is a diagram that shows the amount of anorthite, or basically calcium, in our plagioclase. And you can see the anorthite is represented to the amount of calcium divided by the amount of calcium, sodium, and potassium. And it's plotted against the magnesium number. And our magnesium number is the amount of magnesium over the amount of magnesium plus iron in the given mineral. And we're dealing with mafic minerals, which mean olivine and pyroxene. And what you can see here in the Highlands crust, we actually have our ferroanorthosite, or our fans, forming a vertical trend on this diagram. We then have what are termed the Highland magnesium suite, forming above that and leading down to the bottom left of that diagram, leading into the Highlands alkali suite. If we look then at the ferroanorthosites, we can see that they are mineralogically diverse. The different colors there represent different mineral percentages within our ferroanorthosites. So we have a very diverse suite of materials that we think was the initial crust from the magma ocean there. And to give you an idea of what they look like, you can see 2 hand specimens from the Apollo collection. Now, this vertical trend becomes quite problematic because you can see here in the diagram of anorthite against magnesium number what the expected trend is if you are just crystallizing plagioclase from a magma. We expect it to go to the bottom left. What our ferroanorthosites are telling us is that no, this is a vertical distribution and that the anorthite content of our plagioclase does not change very much. Now, experimentation has shown us that if we have relatively high pressure, and this would require a quenched crust of about 70 kilometers thick, we would end up buffering that anorthite composition in our plagioclase and getting that trend as we see on the diagram. So we do require an early, thick, quenched crust in order to allow this distribution to actually be formed. So from Apollo then, we have our Highland samples that divided into 3 basic suites. We have our ferroanorthosite suite, where you can see this is used as FAS or FAN, FAS or FANs, and these are believed to be the primary samples of the primary crust formed by plagioclase flotation within the lunar magma ocean. The Highlands magnesium suite it represents secondary intrusions. So we had melting of the interior after the formation of the Pharoan and Orthosite crust, and these magmas went up and intruded that fan crust. Then we have the Highlands alkali suite, and these are potentially an evolved M member of the Highlands magnesium suite, and these also intruded the Pharoan and Orthositic crust. So if we look at the Pharoan and Orthosite suite, Apollo 15 was tasked with going and finding some of these ancient samples. They were given the information that these would have been plagioclase rich, and they would be very old because they would represent the actual crust of the moon. So let's just hear a little bit about what the Apollo astronauts from Apollo 15 actually said as they were finding what we term 15415, the Genesis rock.
Oh man, look at that. Look at the glint. Almost see twinning in there. Guess what we just found? Guess what we just found? I think we found what we came for. Crystalline rock, huh? Yes, sir. You better believe it. Yep, sir. Pledge in there. Almost all pledge. Should I see it? As a matter of fact, oh boy, I think we might have ourselves something close to an orthosite. Because it's crystalline and there's just a bunch of just almost all pledge. What a beaut. That is really a beauty. And there's another one down there. Yeah, we'll get some of these.
Now the Genesis rock becomes very important because you can see that it is firmly within the Pharoan and Orthosite field. It is very coarse-grained, consistent with our cumulate from a magma ocean, crystallized slowly, gives you big crystals. And you can see there the hand specimen also of this particular sample. Now, how old is the lunar crust, and how do we age date these anorthositic samples from the lunar crust? And coming back to our rare earth elements again, you can see here we have lanthanum through lutetium, but we're interested in our samarium and neodymium. And remember, 147, the isotope 147 samarium will decay to the isotope 143 neodymium at a constant rate over time. So what we see here then is how we talk about the samarium neodymium chronometer in terms of the rare earth patterns. And we can see here a chondritic pattern, which is a chondritic meteorite pattern, which is flat on this particular representation. And you can see where samarium and neodymium are actually present. If we have a light rare earth enriched rare earth profile, we can see that we have actually decreased the samarium to neodymium ratio. If we have a light rare earth depleted rare earth element pattern, we have now increased the samarium neodymium ratio. So in terms of evolution of these particular isotopic systematics, we're looking at the ratio of 143 neodymium to 144 neodymium. They're both neodymium, they're just different isotopes. 143 neodymium changes because it is radiogenic. It is formed by the decay of 147 samarium. 144 neodymium is stable. And you can see that the evolution line, as time progresses, you can see what happens if we enrich the rare earth element profile in light rare earths. We actually then slow down the increase in the 143, 144 neodymium ratio. If we deplete that rare earth element profile, we would then increase the change in that 143, 144 neodymium ratio. So understanding what the samarium neodymium ratio is of our anorthosites, as well as what the 143, 144 neodymium ratio is, we can then start to get an idea of age, how long that rock has been around since it crystallized. Now, if we then look at the ages that have been determined for our Pharoan anorthosites, we can see here that we've got a range of ages, and our model suggests that these ages should be older than our Highlands magnesium suite and our Highlands alkali suite. And we can use multiple chronometers to do this, but samarium neodymium is a pretty robust chronometer, so we're going to focus on that one for the purposes of this talk. However, we do have issues. If we look at the age range here, it's more than about 200 million years, that it's much too long for a lunar magma ocean to be kept liquid. And also, if you look at 60025, it's on there twice. 60025 has given two distinct samarium-neodymium ages for the same sample. That is a problem, because if it's one sample, it should give the same age no matter how many times you analyze it. Well, one way around the length of time for the defined by the Pharoan and orthosites is to give it an insulating lid. And this is a model that was proposed by Elkins-Tanton et al. 2011 and was then focused more upon by Meyer et al. And what we can see here, that if you have the moon forming, and the orbital dynamics suggest that it was much closer to the Earth than it is now, and we're actually losing the moon at the rate of several centimeters a year as it degrades its orbit. And what we can see then is that if we have an insulating lid or a quench crust coupled with gravitational attraction and friction and heating, we can actually keep the magma ocean alive for longer than 200 million years. But remember, this is just a model. If we look at the Highlands Magnesium Suite, we can see here that we've got a lot of samples that have been dated by the samarium-neodymium technique. They also form a range of ages, and you can see there that the uncertainties are also much different in some samples versus others. You can see that also that the Highlands Magnesium Suite, as typified by 76535, this has this equilibrated texture to it. It's a beautiful rock, but the texture suggests that something else has happened to this particular sample since it formed. Now, if we then combine our Pharoan and orthosite suite and Highland Magnesium Suite samples with samarium-neodymium ages, we have causes for concern. Number one, we have large uncertainties in several of these samples. Number two is that we have different ages for the same sample in a number of cases, both for the Pharoan and orthosites and also the Highland Magnesium Suite. And maybe most importantly is that we have overlapping Pharoan and orthosite and Highland Magnesium Suite ages. So the model that the Pharoan and orthosite crust formed and the Highlands Magnesium Suite then intruded into it is now in question. If we then combine the Highlands Alkali Suite, you can see the zircon ages there also overlap with both the Pharoan and orthosites and the Highland Magnesium Suite. And if the Highlands Alkali Suite is an evolved M member of the Highlands Magnesium Suite, they should be younger than those. So we should see an age progression, and we don't. So we have to go back and look at the rocks themselves. Getting an age date and doing chemistry on these samples is one thing, but how are the minerals related to each other, and what is the texture like? So what we have here are a number of Pharoan and orthosite samples that have been age dated by the samarium-neodymium technique. And what you see immediately, they have a very broken up texture, or what we term brecciated texture. This means that the impacts, meteoroid impacts that have been ongoing since these samples were formed have severely affected the texture of these rocks. Not only have they been mechanically brecciated, they could have been mechanically mixed with other lithologies, because we know from lunar reconnaissance orbiter images that impacts are still ongoing today. So this impact, it has to be taken into account, and how it's mixing these rocks. And yes, we may have a Pharoan and orthosite sample, but it may be made up of different Pharoan and orthosites of different ages, and that may be explaining some of the large uncertainties that we see in the samples, and maybe even the distinct ages that we see for some of these samples as well. For example, 60025. The Highlands Magnesium Suite samples are not faring any better either. 72215 is showing something that is undergoing equilibration. We're starting to see that interlocking texture that we see depicted very well by 76535, suggesting that they have being equilibrated and heated in the solid state, allowing this equilibrated texture to develop. Then we have 15445, where we see a very shocked material where we can't see any defined crystal boundaries as such. They have been blurred due to the effect of this incredible shock through the meteoroid impact. Another issue comes from the data that's been gathered from orbit since Apollo. These are data from the Moon Mineralogy Mapper. This was flown on the Indian Chandrayaan-1 mission earlier this century. And what Carly Peters and co-authors have found from these data is that we have lithologies present in the lunar crust that we simply don't have any representation in our current sample suite. These are olivine, orthopyroxene or OPX, and spinel-rich lithologies, affectionately termed ooze by Carly Peters. Now, magnesium spinel is important because it represents another aluminous mineral. We've talked about plagioclase and we've talked about garnet. And now we're finding that we have magnesium spinel in the crust. So various models have been produced. This could be a direct product of the lunar magma ocean. However, it could also be an impact melt cumulate. You have a large impact, you get a lot of melt. It can also differentiate. Or it could be a reaction between magma and a plagioclase-rich wall rock that could also precipitate this mineral spinel. Now, the significance of these data is the fact that the pixel size from orbit is about 250 by 250 meters. And we're getting definitive signatures of spinel, orthopyroxene, and olivine over these areas. What we don't know is the geologic context of these. Have they been intruded into the crust? Are they a layered intrusion? We don't know. We need to do good old-fashioned geologic field work on the lunar surface at some of these sites to truly understand their origin and how they evolved. This would also include sampling. You could have very strategic sampling by an astronaut that would allow us, as we saw with 15415, that would allow us to get a much better insight into these new lithologies that we knew nothing about until the Chandrayaan-1 mission. Japan also had a mission, Kaguya, affectionately termed Selene, and what we see from the data that they produced is that they focused a lot on the crust. And we see that there is a dichotomy between the composition of the crust on the near side with that on the far side. We knew that there was a thickness dichotomy, as we see with more Mare on the near side and less on the far side. But what we can now see through compositional evidence is that the Selene mission has showed us that the far side crust is more magnesium than the near side. And it may be the magnesian anorthosite rather than the Pharoan anorthosite is the dominant composition on that thicker crust on the far side. Now, this has implications of when plagioclase comes out of our magma ocean. We would have to have a much higher aluminium content in that magma ocean to affect that. But magnesium anorthosite means that it comes out much earlier in the sequence than does the Pharoan anorthosite that we've modeled using the Apollo data. So if we look then at the feldspathic highlands, we can see here are the Apollo data. But we've now got these lunar meteorites which contain an awful lot of highlands materials. They are representative of the crust in the area from which they were derived, but we just don't know which area they were derived from. We can assume far side, but where on the far side, we don't know. So if we then take these two fields, you can see here the Apollo magnesium suite and the Pharoan anorthosites, and we compare those with the data that have come from the feldspathic or highlands lunar meteorites, you can see that these are predominantly Pharoan anorthositic. However, they greatly expand that range of Pharoan anorthosites that we got from the snapshot from the Apollo samples. The problem here is that the Apollo samples have been affected by the Imbrium ejecta. They form a very narrow field that we now know is narrow because we can compare them with these feldspathic meteorites. So the lunar meteorites then are showing us that Apollo gave us a snapshot that was, again, not representative of what the rest of the moon actually is. So the models that have been developed during Apollo now have to be adjusted on the basis of new data. If we then look at what we did learn from Apollo, we can see that the differentiation mirrors that from the big intrusions that we have here on this planet. The ones that we have from the still water are not from a magma ocean. They are a large intrusion of magma. And you can see similarities in the trends there of the minerals in the rock types that come from still water with those from the Apollo samples. If we then compare that with the lunar meteorites, we see that the lunar meteorites show a much more a broader field in terms of magnesium number in our mafic mineral for a very narrow range of anorthite content in our plagioclase, expanding it. So we have to adjust our story now because Apollo didn't tell us everything. The new data are now testing the hypotheses that have been developed, such as the lunar magma ocean, by these new samples and the new orbital data. So in summary, the Apollo and lunar missions to the moon greatly increased our understanding of the moon. We knew nothing really about the moon until we had these samples coming back. However, since then, we've now recognized that we have new samples in lunar meteorites. We've also had a lot of missions, a lot of international interest in our moon now, and a lot of international missions have gone to the moon, and the orbital data shows us that the models previously developed are somewhat lacking. They're being tested, and they need adjusting, or they need to be rethought altogether. We also know that while the meteorites are from the moon, we don't know where on the moon they're from. They're from unknown locations. We need to actually have coordinated sample return from areas well away from Imbrium and the ejecta from that Imbrium basin. And especially, we need to go to the far side and see whether or not we can actually correlate the compositions from these lunar meteorites with those that are collected in situ from the far side of the moon. Now, the geologic context of these new samples is critical for developing these new predictive models. We want predictive models because on Earth we have plate tectonics, and we know what plate tectonic setting to go to get resources. If we're going to use the moon to go further out into the solar system, we need to develop infrastructure, and that means living off the land and defining resources. So understanding these new lithologies, how they fit in to the given framework of lunar petrogenesis is going to be important, and it's going to require geologic field work. And probably the best way to do that is by sending astronauts there who are adequately trained to undertake such an expedition. Now, the geologic context of these new samples is going to be critical for understanding and making predictive models. On Earth, geologists have done field work for many years and have developed these models based around plate tectonics. So if we can recognize a particular setting on Earth, we know where to go and look for specific resources that will fuel our economy. Same as can be said for the moon. The resources will become important as we expand into the solar system. And geologic fieldwork is going to be critical to that. It's going to be required to develop these predictive models. If we can then find out where these resources are, things such as aluminium, titanium, water ice, so on and so forth, we then can start to develop an economy behind that. Because it's not NASA's job to go out and mine regolith. This can be brought in as a commercial venture. We can start to expand the space economy. We can start to then bring in private industry, which is going to be employing people and going to be starting to hiring new people to do that, and thus creating jobs that are going to be a necessity as we become a spacefaring species. As we expand to the moon to go on to Mars, the resources on the moon can be used to enable Mars. For example, if we look at building structures on the moon for infrastructure, 3D printing becomes important, and knowing that there's titanium and there's aluminium and there's silicon and there's water ice on the moon becomes important. Being able to harness these resources requires commercial participation. So NASA can then expand onto Mars, but can then buy services and the materials required in order for example, water is a good radiation protection. We can sheath a spacecraft in water. Launching it from the moon, it's much cheaper than launching it from Earth. We know that the water ice is there now. We can then expand upon that. So by building a spacefaring species, we then enable a new sector of our economy. We expand that space economy. And with the USA being in the forefront of this, this is something that we can lead the world to do. And I think it's important that we use the moon as a stepping stone to do that, although I hate the term stepping stone. It becomes an enabler to do that. The moon is an enabling asset in order to not only go on to Mars, but to expand our space economy into something that is robust and growing, so that graduates from my university, when I ask them, what do you want to do after Notre Dame? They can say, I'm going to go work on the moon. And that becomes science fact, not science fiction.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
6, 5, 4.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument, you're slapping it on a rocket, and for the next 8 minutes, the explosion from that rocket is following you into outer space. Vibrating you, shaking you. Everything that goes into outer space has to live through this environment and work once it gets there without having someone come to fix it.
That's how long it will take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail-biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we unfold Webb's solar panel for power and our Huygens antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days, half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield pallet, then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a trim tab to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, of approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton material, about 1 to 2 thousandths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy a side. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sunshield release mechanisms need to fire on cue. 107. They free the 5 sunshield layers, allowing them to extend as the mid-booms deploy.
Sunshield fully deployed, we start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, a secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
For every generation, the moon has been a beacon of tides and time, of dreams and destiny. For many across NASA and around the world, it has been calling to us. It has been the daily efforts of thousands whose quiet resolve has pressed us forward and prepared us for this next moment. We don't just stand on the shoulders of giants. we stand shoulder to shoulder with the generations of dreamers and doers that have navigated every phase of preparation. To every hand that has added a fingerprint to what we now call Artemis, thank you. All of your hard work will soon be realized. Today, the moment of return to the moon has never been closer. The path forward never so clear. The number of those committed to the Artemis Accords continues to grow. The commercial lunar delivery missions that will pave the way are nearing launch. And as NASA's Artemis 1 stands fully stacked, the hardware for our future human missions to the moon is well underway. Are there challenges ahead? Certainly. But this is our path to Mars. We are about reaching further into the unknown and learning how to live on other worlds. Because the farther we reach, the greater we grow. And as history has taught us, the greatest of these benefits are fully realized and utilized here. With the launch of Artemis 1, we say we return to the moon for all humanity.
The Space Launch System is the next generation heavy lift rocket for NASA that's going to take humans and cargo missions farther into deep space than ever before.
SLS is massive. It's the size or larger than most buildings. We're talking about flying a skyscraper, essentially. So we need a lot of propulsion. A big portion of it is really just the propellant that we need to get that heavy weight off the ground.
These rockets need to go 5 times the speed of sound to get out of the atmosphere. And what happens is that the air acts as a can crusher, and it's trying to crush that vehicle. So what we have to do as aerodynamicists is quantify what those forces are doing to your rocket.
As we're testing in the wind tunnel, we're looking at the pressures that the body sees all the way up. That really just determines how strong that shell needs to be. We need it to be nice and strong, but not too strong, because if we make it too strong, then the rocket is too heavy, and that takes away from some of the payload that we can fly into space.
Every time we design a new launch vehicle, the airflow is different, so we have to test.
Our first test launch for SLS will be going around the moon and back again.
We are building that vehicle right now. It's being stacked up as we speak, and we'll be ready to fly in 2020. When the Space Launch System flies, no other rocket will be able to take such heavy payloads into space.
Our ability to carry all that heavy equipment up there is incredibly important, and this is the way that we're going to do that.
We're going to be able to take humans to Mars, but the international community is going to have to come together and collaborate in a unique fashion. It's not just governments, it's all of the commercial industry that is really blooming right now, and even private citizens. We're going to rely on all of that in order to get humans to Mars.
NASA, while we've developed a lot of the technology that's going into a lot of these rockets, and our government is funding most, if not all, of this work, either directly or indirectly, we need those partners so that we can keep pushing the frontier.
Winter 2018. It's cold out here in the distant reaches of the solar system, close to 4 billion miles from Earth. And NASA's New Horizons robotic spacecraft is alone. But it's intimately connected to a team of human scientists and engineers back on Earth. It's their passion, skill, and commitment that powers the mission, just as much as its plutonium fuel. Using approach imagery, they're making final TCMs, trajectory correction maneuvers, to take it as close as 2,200 miles to its next target. After a journey of almost 13 years, New Horizons is closing in for a January 1st, 2019 flyby of a tiny world. It's officially known as 2014 MU-69. Now, this icy Kuiper Belt object is being informally called Ultima Thule, honoring the mythical land beyond the edges of the known world. And Ultima is the most distant and most ancient object ever encountered by any space mission. Those long years in flight have seen the awesome success of the 2015 encounter with the Pluto system.
We knew it was going to be scientifically rewarding. We had no idea it was going to be so beautiful.
But just 10 days before closest approach, New Horizons had its own Apollo 13 moment, when the mission ops team had to diagnose and correct a computer malfunction under the most extreme time pressures.
My heart did another flip. I thought, oh my gosh, I really hope it's not that.
That was almost a worst-case scenario.
Exploring the outer solar system is an endeavor in which the United States has led the world. But targeting the close flyby of Ultima has relied on support from nations and space agencies across the globe. It's taken the Hubble Space Telescope and the European Space Agency's Gaia satellite, powerful telescopes in Hawaii and Chile, volunteers and local governments in South Africa, Senegal, and Argentina, and an ambitious night flight aboard NASA's SOFIA Flying Observatory, deploying out of New Zealand.
The spacecraft has the capability of continuing working for several decades. January 1st of 2019 is just the beginning of another era of discovery for New Horizons.
Out here, in the eternal deep freeze at the edge of the solar system, are clues to how Earth and all the planets began and evolved.
This is even more challenging with Ultima Thule because it's another billion miles further out, it's considerably smaller, it's a very, very faint object.
Climbing Earth's tallest peaks requires the ultimate in passion and perseverance, technical skills, and the age-old longing to explore and achieve. Now, approaching Ultima Thule, this is the human story behind one of NASA's most ambitious missions, summiting the solar system.
Some people might think that there's not much happening after Pluto. We flew by, we got all the data down, but we are in the midst of planning. We're planning for our next encounter.
New Horizons is flying on past Pluto another billion miles to make a flyby on January 1st, 2019 of a small Kuiper Belt object.
For now, this KBO's official name remains 486958 2014 MU-69, or MU-69 for short. But in March 2018, it got its more evocative informal nickname, Ultima Thule, or Ultima, thanks to a public naming contest.
MU-69 is going to be a really interesting object because it is representative of the building blocks from which planets were formed.
2014 MU-69 is by far the most primitive and pristine object that we've ever had the opportunity to fly by. By virtue of its small size and its isolation, we believe that it is probably the closest we've ever been to something like a primordial building block of the planets.
So we've got the arrested development of the solar system waiting there for us to explore.
One of the most challenging aspects of the flyby is simply targeting the flyby. Never before has a spacecraft launched to a target that's not even discovered at the time of launch, much less tried to home in on something where we'll only have known about it for a small number of years and only tracked it through about 1% of its orbit around the sun. And yet we have to intercept it potentially even closer than we did with Pluto.
New Horizons sped by Pluto just 7,800 miles above its surface. But if all goes well, the spacecraft will skim only 2,200 miles over Ultima.
We are planning the sequences, what science we're going to do, or even planning ground-based observations to figure out where the target is.
Success will be powered by rocket science, but also by efforts much more down to Earth.
Just completed a huge occultation campaign in Senegal and Colombia on August 4th, 2018.
It was a huge effort. We sent 21 telescopes to Senegal. So we had 21 different teams, each with 2 observers from the United States, an observer from Senegal, someone who was knowledgeable in astronomy, a driver, and a military escort. So that's a lot of people scouring the countryside of Senegal to get in the shadow path. If I'm the star, and this is MU-69 moving in past you, and you're the Earth, and observers are on the Earth, as MU-69 is moving in front of me, the star, it's blocking the starlight. And so if you were looking at the star, you would see it dim out over time and then come back up as MU-69 passes in front. You are effectively in the shadow of the starlight.
Kathy makes it sound simple, but the star which Ultima Thule will pass in front of is close to the center of our Milky Way galaxy, one of the starriest places in the sky. To help in understanding the incredible 4-dimensional problems the astronomers faced, with time a consideration as well as the 3 dimensions of space, it helps to think of a phenomena that's more familiar to many of us. The total eclipse of the Sun that crossed North America on August 21st, 2017. Then, the star which creates the shadow is our local star, the Sun. The occulting object is the Moon. You had to be in the right place at the right time with the right weather and clear skies in order to catch the shadow. But if you were in the right place at the right time, you were treated to one of nature's most spectacular sights. For the men and women of New Horizons, things were a lot more complicated. In a solar eclipse, the relative closeness of the Sun and Moon to Earth means there's a wide area seeing a partial eclipse, and just a small region that witnesses totality. For the MU-69 occultation, the distances are much greater. The star emitting the light is some 25,000 light-years from Earth, and MU-69 is 4 billion miles away. That means the starlight is effectively a point source and casts a shadow on Earth that's only as wide as MU-69, about 19 miles across. And it passes over any one location in less than 2 seconds. Identifying which star Ultima will pass in front of takes 2 of Earth's most powerful astronomical assets, the Hubble Space Telescope and the European Space Agency's Gaia satellite, with both pushed to the very edge of their capabilities. It was Hubble that a team of New Horizons researchers used to discover tiny Ultima in 2014. Extrapolating its orbit from several repeat observations, they then used specially approved early access to the incredibly detailed Gaia dataset of more than 1 billion stars to figure out exactly which star MU-69 would pass in front of. It's a dim 13.4 magnitude star, and even finding the star that's going to be occulted in the night sky is hard. The observers used constellation patterns to target their telescopes at that dim star, somewhere between the teapot, with its bright star Nunki, and the teaspoon. Above Nunki, they used another pattern they nicknamed Evil Rudolph, with one bright star as Rudolph's nose, 2 eyes, and the antlers, pointing to the actual target star close by. Another challenge. Unlike the position of Earth's moon during a solar eclipse, MU-69's orbit around the Sun is still relatively uncertain, since the object was only discovered, by Mark Buoy in fact, in 2014. That's not very long to track its speed and position. Although Ultima's exact size and shape is still uncertain, the best estimates are about 30 kilometers across, between 18 and 19 miles. For the August 4th eclipse, the shadow path would only be over land and accessible in West Africa and the top of South America. The green line is the predicted center of the shadow path. The dark blue lines show the edges of MU-69's shadow, and the yellow lines show the limits of telescope coverage, allowing for uncertainty. The team in Senegal, also led by Mark Bowie, had 21 telescopes. To maximize their chances of capturing the shadow, the observing teams would be placed 4 kilometers apart along those light purple lines in what they called a picket fence pattern. Given the uncertainties of clouds and rain, the team researched more sites than they had telescopes in order to be able to change deployment locations depending on the weather. And of course, they'd be looking for a less than 2-second shadow in the dark of night. Weather wasn't predicted to be completely favorable in either Colombia or Senegal, which was why Mark was hedging his bets by deploying telescopes on both continents.
Just about any other time of year, Senegal would be a lovely place to go do an occultation. But as luck would have it, we were there kind of at the middle of the rainy season for Senegal.
The anticipation was that this was going to be a problem, and it was.
In late July, the Americans arrive in Dakar and check into a newly built airport hotel for the first couple of days. They met their Senegalese colleagues and astronomers from France and practiced their observing protocols.
And we got a couple of practice nights in. We got to set up the equipment, make sure it made the journey all the way from Boulder, Colorado to Dakar, Senegal safely. We set up the systems and tried them out. Everybody got to practice with them.
So our Senegalese teammates were definitely enthusiastic about helping us and participating in this event. I think they all really appreciated that this was an incredible opportunity to take part in mission-critical observations for NASA. I mean, NASA has a worldwide brand. Everybody recognizes it. So it wasn't hard to make those connections.
I was very intentional in setting up these expeditions this year to involve the locals as much as possible. In Colombia, we were tied into the amateur astronomy networks and everybody that they knew there to get help. In Senegal, I reached out and said, look, I want your people as equal partners on these teams.
The Senegalese colleagues that we worked with, they were outstanding. They all had a really strong interest in science and engineering, and they were dedicated to helping us get the data.
From the very first day that we contacted the Senegalese, through the embassy, our project crossed the desk of the president of Senegal. He knew about it. He saw it and in an instant said, I want our country to be involved in this. And he put his best people on it.
Mark had been up late, advising the observing teams and speaking to TV journalists.
I got up at like 2 in the afternoon from being up the previous night. I'm trying to get everything organized, everybody ready, and all sorts of crazy stuff. And Adriano Campo from NASA headquarters comes in and says, the president wants to meet with us. And then a half an hour after that, we're all on buses going down to the presidential palace.
Suddenly there was a message on Slack that said, oh, hey, we need to go meet the president, put on your best clothes.
So we are about to go meet the president of Senegal. And the palace grounds were absolutely beautiful.
Thankfully, I had some decent looking shoes. There are a lot of people who just had like sneakers.
Of all the expeditions I've done, this is the first time I have ever had to meet with a head of state as a result of an occultation. The atmosphere there was just really amazing. And all of the people that were involved, all being on board with this kind of effort and doing what it takes to make it a success.
After the ceremonies, it was time to head north to the observing sites. But the high-level attention and support continued.
So we definitely had a full convoy led by police escort leading us the whole way. If there was any traffic that looked like it had potential to hold this group up, they were told, nope, you let this group through. So we made very good time.
So we just arrived in Luga. We're gonna go out and practice tonight, and then tomorrow night will be the occultation. So more than half of our group has come to Luga so that we can be spread along the occultation path.
In Luga, the planning intensified, with Mark running through which team would go where, and the Senegalese partners detailing logistical support, ranging from adequate drinking water to protection against snake bites.
In Senegal, we had 21 stations deployed out in a picket fence, roughly over about 150 miles or something in northern Senegal.
We wanted a very tight picket fence. Each system was a cut across the shadow of Ultima Thule as cast by the star.
At last, they set off for occultation night, August the 4th, Universal Time, hoping for clear skies. But after all the preparations, not even presidents or NASA can control the weather. Most teams returned to Mark, who was anxiously waiting at the hotel, without having seen the occultation star blink out because of clouds or even rain.
I knew as people were filtering in, I knew what my result was. We got clouded out.
I'm sitting there and team after team is coming in saying, clouds, rain, no.
All the people with me were so disappointed, and I felt really bad for them.
We spent so many months working so hard for this one moment, and it's not looking really great.
Aaron Resnick had spent much of the first few days on the phone, trying to reach someone back in the States to help fix broken equipment. Like everyone on the team, he'd had to juggle travel, logistics, and keeping hydrated, but he also made time to engage some new friends. Peter Tamlin from Sweary was Aaron's observing partner.
Aaron Resnick and Peter Tamlin come in and said, hand me that stick and said, you've got to look at this. That was amazing. And he says, we got it, we got it. They were absolutely sure that they had seen it and the star had disappeared.
Took a quick look at the right time and, oh yes.
We were all looking for Amanda to be analyzing the data, and then she said, yeah, I've got it. And we rushed over to her computer screen, and everybody was crowded around looking at it, and you could see high points where the star wasn't occulted by MU69, and then it would drop down and you couldn't see the star, and it went a few points and then it came back up. So it was just a really clear signal that we got an occultation.
Out of the 21 stations that we sent to Senegal, 2 got data that were unaffected by clouds for the minute around the time of the occultation.
That is going to help us be able to navigate the spacecraft successfully to Ultima Thule, because that gives us another point to add to our arsenal of where Ultima is.
It was absolutely the best possible result that we could get out. It gives us a lot more confidence that we're on the right track with the spacecraft trajectory as we know it right now.
So, in the final months of 2018, New Horizons was perfectly on course for its next target. Expectations were building, just like they'd been in 2015, as the spacecraft closed in on Pluto. Before New Horizons arrived at Pluto, NASA's last first-time visit to a planet had been 26 years earlier, in 1989, when Voyager 2 arrived at Neptune. Many future members of the Pluto mission had been at JPL, watching the images of Neptune and its moon Triton scrolling up line by line. John Spencer had longer hair then, but already always had a camera at hand. With no new missions to the outer planets underway, many wondered what would be next. 2 years later, the U.S. Postal Service issued a set of stamps commemorating America's visits to the innermost 8 planets, and honoring the spacecraft that had reached them. But the stamp for Pluto read, "Not yet explored." That rankled planetary astronomers at JPL and added to the ambition of Alan Stern, Mark Buoy, Fran Bagenal, and others who, in 1989, had already dubbed themselves the Pluto Underground and started pushing for a first mission to the last planet. Finally, in early 2015, a spacecraft began approaching Pluto.
In the months and weeks leading up to the Pluto encounter, every day was exciting. Every day brought new information about Pluto and Charon and the small moons. We would have new views of Pluto, unlike something that we had ever seen before. I felt like I was a kid in a candy shop. I would go to work, 7 days a week, be there all hours of the day because there was nowhere else that I wanted to be. That was where the excitement was happening. That was where the new data was coming down. We were seeing something new that we had been waiting more than a decade for. And it was really exciting every single day.
The approach to Pluto in anticipation of the flyby was an amazing period of time. I've been working on Pluto for decades, basically spent my whole life and career working on studying this distant world. And to finally be able to open the box and find out, one, if was I right in all of the research that I've been doing, and what else is going on there that our imaginations fail us in figuring out what's going on Pluto.
It was very hectic. Every day we would get a little bit more data on Pluto up until the encounter.
I was kind of expecting maybe, a dead world, and what we got was anything but. And every time something else came down, it was just another triumphant moment.
After waiting so long, we were so keen to see what it would look like. And it was kind of funny, each team meeting, they'd show a picture of Pluto. This is the latest. And it was, to be honest with you, a fuzzy blob. And then a slightly larger fuzzy blob. And then a little bit bigger fuzzy blob. And indeed, it really didn't look like much until we really got there and we really got to see the pictures.
All was going well, but with the forethought that characterized the entire mission, they'd planned what they called a fail-safe image, a final full-frame picture from the long-range camera LORRI to be sent back before the closest approach, just in case something went catastrophically wrong. In the months leading up to the encounter, they'd carefully searched for hazards near Pluto, a ring or a small moon, or even grains of dust that could collide with the spacecraft and end the mission. They thought their close approach trajectory was clear, but there was always that unknown unknown. Alan Stern, with an eye towards a dramatic reveal, charged a small group with taking that fail-safe image and working on it in secrecy overnight to be ready for an early morning science meeting, after which it could be shared with the whole world. One of that team was Alex Parker.
There are moments that will, live forever in my memory as recognizing that I'm part of something that is only going to be witnessed one time. This first revelation of Pluto.
The group of us got together: John, Alex, Todd Lauer, Carly Howlett, myself.
My primary work is on the color imager of New Horizons, and so there was a lot of work going into the calibration so that when we got the images back, we could quickly process them and release them to the public and to the scientists so that we could get the most out of them.
So it was myself and a few other members of the team that were given access to the first best look at Pluto that night before encounter, that last fail-safe image that we took on approach, and we're tasked with combining it with our earlier color image to reveal to the world at 7 a.m. the next day.
And so the five of us were there, and then Hal Weaver was sticking around to download the image. He wasn't originally even going to see it, but he sort of downloaded an image, and he brought it to us on a flash drive, and we put it in, and we looked at it, and like, wait, what the hell is that?
The spacecraft had sent back the correct image. Simple operator error down here on Earth called up the wrong picture.
And it turned out to be an image of Charon that we had linked the day before. It looked nothing like Pluto. If that was what Pluto would look like, we would have been very disappointed. But then we went back and actually found the correct image. And so we first saw it on Hal's monitor in his office.
It was incredibly exciting, and I'm British, so we don't sort of use words like incredibly very easily. So it was incredibly exciting. It wasn't like the Voyager days when you have a line at a time. All of a sudden, this image just comes up on your screen.
I remember just walking back from Hal's office, my arm was just shaking like this, because I've just been waiting so long for this picture, and we finally saw it.
The failsafe image was so many things. Yes, it was brown, and you get something from the color, and it was also had so much going on in the image itself. You were trying to, like I said, you're trying to sort of decipher all of those things simultaneously, and I think everyone was, and sort of doing geology on the fly and doing chemistry on the fly, and just coming up with wild ideas. What do you think this could be? What do you think this could be? And sometimes you get caught up just sort of staring at the images and then realize, oh no, quick. We're supposed to be working on something else.
For that evening, the 5 of us were the only people that had ever seen Pluto up close. And so there was that period in time in which myself and these others were privy to this knowledge of what that last world looked like.
Not only was it one of the best images we've ever had of Pluto in terms of spatial resolution, but it also was a very personal thing for me. It felt like you were on the cutting edge of discovery.
I certainly felt shocked when we first saw that image.
Around 5 a.m. on July 14th, the mission team left their hotel for APL. After 26 years of effort, Alan greeted his colleagues as their long day began.
Well, how about a Pluto flyby, everybody? So last night, the spacecraft went over the hill. We'll be hearing from it about 9 p.m. Eastern time tonight. In the last transmission from the spacecraft, everything was good on board, and we got down our last image, which is, of course, the Pluto LORRI full-frame image. There's a small team of people that worked very hard overnight till 3 a.m., and I'd like them to stand up for some thanks.
At this time, the newly processed high-res image was still embargoed, waiting for Alex to release it to Hal and the world.
And then we got to be there when it was revealed to the rest of the team and the rest of the world and see how they responded. And that was really a spectacular feeling.
Alex hit send, and the image sped to Hal. Carly was super pleased.
History.
But as often happens, computers don't work quite as fast as you want them to. After 26 years, the team was getting understandably impatient.
Oh, I set the exposure time wrong.
And I think it's the iconic image that came out of the encounter. The reason that I think it's so wonderful is it's got amazing spatial resolution. You can tell so much about Pluto just by looking at that image. You can tell things about the geology and the topography and the activity and so many things that we didn't know about Pluto existed until we had that image. It's been a single pixel really for a long time, and so you sort of had that feeling of disbelief.
So this is my chance to say a little something. 22 years ago this summer, a few of us were at a conference in Flagstaff to put together the case to go to the Pluto system. Many of us made predictions. And with this image, I've been proven right because my prediction was what we would find was something wonderful. How about that?
We knew Pluto would be good, but I don't think any of us expected it would be this good in terms of the scientific riches.
Sometimes good things come in small packages, and I think that the dwarf planets have been vindicated this morning.
They were thrilled by the high-res black and white, but then it was time for the color image that Carly, Alex, and their small group had worked on so hard overnight.
It was an exciting thing to see this black and white world move into a color space.
So we knew it was going to be scientifically rewarding. We had no idea it was going to be so beautiful.
I saw a new side of people because it was just such a new experience for all of us. Just the sheer joy of of being able to be present for the newest and the latest, and to make these groundbreaking discoveries. That's my favorite part, right there. I did color-wise.
When that first picture came back and showed that gigantic heart on Pluto, oh my gosh, I can't explain the feelings that you got.
I think my favorite picture from the encounter is the one that shows the full view. I think that really stands out. When I think of a picture of Pluto, I think of a sphere with a heart.
We saw this spectacular view of the surface of Pluto with all the mountains, the plains, the high elevations, the different colors.
You know, you have people that have spent decades trying to understand the solar system and its evolution, and they know more than anybody else on the planet, and yet they're sitting there saying, wow, what is that? I mean, that's just really special.
I think I was surprised most as a scientist by how complex Pluto looks. And I remember thinking that even when the very first images came back, and how varied the terrains are.
You thought, after all these years of such hard work, this is all worth it, even if we only got that one image.
That was like a wow moment. Everybody just went berserk.
I was utterly amazed with the complexity of the surface. We had no idea that it was going to be as exciting as it was.
Will Grundy started sharing details of Pluto's surface composition, and the team began to realize the incredible richness of the data that New Horizons had captured.
This is false what you see here is that there's just an incredible range of compositional diversity.
Well, when those first images came back, I remember thinking just how proud I was that we had pulled this off, and that it had all worked, and that people's over a decade, 15 years of nights and weekends and everything else it took had gone so smoothly. And more than anything else, that's what I think I was thinking about on the morning of the flyby. Just pride in the 2,500 Americans that had worked to bring this from an idea on a sheet of paper to a spectacular scientific success.
One of my favorite pictures from that first day is a picture of a dozen geologists up against the big display of Pluto, pointing out all these things. Oh, is that this? Is that this? Doing instant science in that first half hour.
While the science room was abuzz, the Mission Operations Center was empty, except for a cleaner. New Horizons was alone in space, running through the pre-programmed commands that had been radioed up a week ago. The spacecraft was busy with some 236 separate scientific observations. All 7 of its instruments were focused on Pluto and its 5 moons. There was no time to turn the antenna back to Earth. Although New Horizons was alone in space, it was, of course, very much on people's minds at APL and those watching NASA TV coverage around the world. Alan led a countdown to the actual moment of closest approach.
5, 4, 3, 2, 1, New Horizons at Pluto 2015.
Then it was time to cancel that stamp from so many years before.
A long time ago, the United States issued a set of stamps for the exploration of the planets, honoring all the spacecraft that have been first to each and every planet. And we have a copy here of the stamp that was issued for Pluto because it was the only planet that was not yet explored. This is from 1991. You can buy these stamps, but about 2 minutes ago, we just made it obsolete.
But for all the excitement of the fail-safe image and that moment of closest approach, the real proof that New Horizons had gathered the goods at Pluto would come that evening. That was when the spacecraft had been programmed to phone home, reporting its status. This was the scene in Mission Control, waiting for Mom, Mission Operations Manager Alice Bowman, to confirm the receipt of a signal verifying that all had gone well.
We are searching for frequency. Stand by.
Had New Horizons run into undetected debris and dust? Had it survived closest approach?
Just go ahead, autonomy.
Autonomy is very happy to report nominal status. No rules have fired.
Okay. Go ahead, GNC.
GNC is nominal, all hardware is healthy, and we have a good number of thruster counts.
Copy that. GNC is healthy. Okay. PI, Mom on Pluto 1. We have a healthy spacecraft. We've recorded data of the Pluto system, and we're outbound for Pluto.
With a healthy spacecraft and the expectation of a bonanza of new science, the entire New Horizons team, including NASA's VIPs, headed over to APL's largest auditorium for a broadcast press conference.
Ladies and gentlemen, please welcome New Horizons and the team.
On this occasion, the men and women of Mission Ops were feted as rock stars. Engineers being recognized as equally important to the mission as the scientists. NASA's then Administrator Charlie Bolden, a former astronaut, made congratulatory remarks, and the engineers went back to work. Astronaut and Associate Administrator John Grunsfeld shared a tweet from President Obama. Glenn was feeling good. Alan answered questions. Alice took a bow. America had finally completed the reconnaissance of the classical solar system. 50 years to the day after Mariner reached Mars, New Horizons had a successful encounter with Pluto. July 14th was finally over, but a new phase of the mission was just beginning.
For us, July 14th was when all the action happened and it was a time to celebrate. But then July 15th was when the real excitement began because we actually started getting to see what New Horizons observed.
I would say every day we got a new surprise, but every day we got 10 new surprises.
You would have a whole bunch of people gathered around a given computer screen, and you knew something was going on, so of course you glommed onto that and looked, what is this? What's the new data?
And everyone would just stay late, would get in early. We wanted to come in, we wanted to see what new images, what new discoveries had been made overnight or earlier that morning.
All the pictures were different and they were all spectacular.
Pluto is a collection of the world's coolest national parks all put onto one planet.
Weird ices and flows. Yes, there were impact craters, but they had this rim of frost around them. And then we had cracks, and then we had this brown, oily, gunky stuff on the surface.
There's this large glacier on Pluto, and there's a huge canyon on Charon, and that the North Pole of Charon is red. And what does that mean?
All of it told these stories that were either not necessarily what we expected or so far beyond what we expected that, no one would have seen it coming.
Some people are lucky that they discover one thing in their entire career, and that's an amazing thing. I felt like we were discovering one thing a minute.
The moment when one of my colleagues walked into the room carrying his laptop and saying, "There's haze," and flipping it around and seeing that first departure image that we got where we could see the loop of light around the outside. And this was something that none of us really expected. And so I was then the one that walked into the atmospheres room with a laptop to show them the image, and to see them just hit the ceilings with joy and excitement and, worry a little bit about their heart health. That was quite a moment.
The pace of science I've never seen before or since.
We're all human, and we all wanted to, see what was the newest and the latest, and that excitement was just really evident in every room.
Being in the room when we got the first color image down that showed that the two halves of the heart were different colors, and that was our first clue that they were two very different kinds of terrains. Just moment after moment like that.
It was